Hello, this is Lab 2, Charged Tape Revisited. In this lab, I revisited the charged tape experiment from Lab 1, but used a more sophisticated model for the electric force. The purpose was to replace the previous point charge approximation with a distributed line charge model. Instead of assuming all the charge was concentrated at the center, I modeled each tape as having charge evenly distributed along its full length. The goal was to determine how much charge is required for one tape to float above another when the electric force balances gravity. And using the improved model, I found that each tape required approximately 2.28 times 10 to the negative 8 coulombs of charge to float, which was a significantly larger value than the estimate from the point charge model in Lab 1. This lab relied on Coulomb's law, gravitational force, and the equilibrium condition. Coulomb's law states that the electric force between charges is proportional to the product of the charges and inversely proportional to the square of the distance between them. The gravitational force on the tape is given by F equals mg, where m is the mass and g is gravitational acceleration. The tape floats when the upward electric force equals the downward gravitational force, meaning the net force is zero and the system is in equilibrium. The experimental setup was the same as in Lab 1. Two charged U-tapes were created using adhesive tape, and each tape had a length of 0.2 meters. Therefore, using the linear density of 1 gram per meter, the mass of one tape could be estimated to be 2 times 10 to the negative 4 kilograms. In the experiment, one tape was suspended above another, and the separation distance between them was adjusted until the upper tape floated. The equilibrium separation distance was measured to be about 0.021 meters. The system is the floating top tape, and the surroundings are the lower charge tape and the Earth, which provides gravity. Using the measured mass, the gravitational force was calculated as Fg equals m times g, which equals approximately 1.96 times 10 to the negative 3 newtons. At equilibrium, the magnitude of the electric force must equal the magnitude of the gravitational force. The electric force can be written as Fe equals Q times E, meaning that the force depends on the charge of the tape and the electric field produced by the other tape. This equilibrium condition is what allows us to determine the required charge. However, instead of using a simplified point charge formula like in Lab 1, this time the force was calculated using a distributed charge model in VPython. In the computational model, I used the observed mass and separation distance from the experiment. Each tape was represented as 40 evenly distributed point charges to approximate a continuous line of charge. The electric field at each segment of the top tape was calculated using Coulomb's law, and nested for loops were used to sum the contributions from every segment of the bottom tape. The net electric force was found by adding all of these pairwise interactions. I began with a trial value for Q based on the thin rod estimation, and then adjusted Q until the computed electric force matched the gravitational force. In other words, I used trial and error. The nested loops shown here perform the main physics calculation. For each small charge element on the top tape, the program calculates the electric field due to every element on the bottom tape. The force on each segment is computed using F equals QE, and all contributions are summed to determine the total electric force. It's worth noting that interactions within the same tape are ignored. When Q was adjusted to approximately 2 times 28 times 10 to the negative 8 coulombs, the computed electric force matched the gravitational force to within numerical precision. This confirms that the tape floats when electric force balances gravity. Compared to Lab 1, this required a noticeably larger charge. This shows that modeling assumptions can significantly affect quantitative results. This turned out to be the main result of the lab. Now, possible sources of error include approximating a continuous charge using only 40 discrete charges, assuming the charge is evenly distributed, ignoring air resistance, and possible charge loss due to handling or things like humidity. If each tape had been modeled as a single point charge, the estimated charge would have been much smaller at about 9.8 times 10 to the negative 9 coulombs, as we saw in Lab 1. The line charge model requires about 2.3 times more charge to produce the same floating condition. These estimates differ because the point charge model assumes all charge is concentrated at the center, which underestimates the average separation between charges. The line charge model accounts for the distributed geometry of the tape and is therefore more physically realistic. And for that reason, the larger charge estimate from the line charge model is more likely to be closer to the true value. Thank you for watching.